So not only is this lesson quick, it's also very easy. And surprising. There is no catch. You'll see how ridiculously easy this is. There you go. So we are going to talk about E some more. Anybody remember what E is?
Well, what is it?
E?
Rejection.
It's doing something.
Wait, go on.
I don't know the rest of it.
One to the negative 10.
1, 2.
Mark.
No, 2 points.
You had like a whole sentence about it, right?
Yeah, what is it?
0.7.
Something that, like, no, it has something to do with some history. Andrew Jackson's
Yeah, so what's the number?
2.17?
No.
7.1.
18.
I don't know.
2.17.
Oh, you're cheating.
Or 2.71.
Right.
2.7 and then 1828, 1828.
You got
45,
6 more.
90.
45, 90, 45.
45, 90, 45. Very good. And you don't really need to know that. You need like 2
Make
points.
an extra credit.
One small.
We are going to talk a little bit about the natural exponential function. That's the fancy term for E. We're going to differentiate that bad boy. We're going to integrate that bad boy both in the same lesson. Yes, this is going to be fun. It should be. This is awesome. This is math at its finest. And then, of course, today, be kind whenever possible, and it's always possible. Anybody know who said that?
Not Alex Butchess?
You.
Mike Reed.
No. Well, I did just say it, yes. Technically speaking, I did say that, but I didn't say it originally. Good.
Sure.
Nice job. Okay. Dalai Lama. So here's the natural log function, which you already knew, passes through the point 1, 0. It's ever increasing, also known as strictly monotonic. Very good, because it's always increasing. And if we take the inverse of the natural log function, we get the e to the x function. Okay. We talked already about where the number e comes from, but now we're generating a function by taking e and raising it to a variable. Okay, so these are inverses of each other. You plug e to the x into the natural log, you get x. If you plug the natural log into e to the x, you get x. They're inverses. We're good to go. Okay, notice this one passes through 1, 0, therefore that one passes through 0, 1. This is also constantly increasing, so it's also strictly monotonic, which you would expect because they're inverses of each other. What else? It's asymptotic to the, I think I got this in a later slide. Yeah, that confirms that. We knew that. All right, great. Hey, solving equations. It's been a while since we've done that. I think that's advanced algebra or pre-calc? Pre-calc. Okay, so we're going to solve that by taking the natural log of both sides. This isn't logarithmic differentiation. We're not differentiating. We're just trying to solve for x here. Take the natural log of both sides, and I get that. Do you know what the natural log of 7 is?
No.
Good. I wouldn't expect you to. If you did, that would be a little weird. So we're going to leave that as a natural log of 7. What's a natural log of e to the raised to the x plus 1? X plus 1. Good. So the right side simplifies to that. Solve for x by subtracting 1 from both sides, and we get that. Why did I write this side that way? Why did I put the negative 1 out in front? Any guesses? This is kind of trivial, but
Like to avoid confusion with ln 7 minus 1.
beautiful. Did everybody hear that? I don't want you to mistake that as being the natural log of 6. 7 minus 1. So move it out in front. It's not a big deal, but just thought I'd mention that. And then if you had your calculator, you want to plug and chug into your calculator, you could get the approximate value of 0.946, because remember, we're AP and we round to 3 decimal places. Always. Okay. Little pre-calc review there. This is what I started ranting about, but I knew I had it in a graph. The domain of e to the x is negative infinity to infinity. You could tell that from the graph. It goes all the way to the left, all the way to the right. It goes up when you're going to the right. It has a range of 0 to infinity. It's asymptotic to the x-axis, meaning it gets closer and closer, but never touches the x-axis. That's why this is a parentheses and not a bracket. Can't be 0. It's continuous, it's increasing, it's strictly monotonic, it's 1 to 1, blah, blah, blah. It's concave upward. And these things we already knew from looking at the graph. If you go very far to the left, it's going to get closer and closer to 0. If you go very far to the right, it's going to keep going up and up and up to infinity. So pretty easy ideas that you could have gotten from just looking at the graph of e to the x. And I think in pre-calc you also looked at like 2 to the x and 4 to the x and that kind of business, right? We're not going to do much of that. We're focusing on e to the x. So now we want to differentiate and we want to integrate. This is going to be fun. Really, it's going to be fun. All right, we good? No, still writing? Okay. Jimmy, you were also at DECA yesterday. Good job.
Thank you.
Whole team made it?
No, it's you qualify as like individuals. Like you can't qualify as the team.
It's not like cross.
Did you qualify?
Yeah.
Did you qualify?
Yeah.
Oh, good. And you signed? Congratulations.
Thank you.
Pretty impressive.
He's still soft.
Where?
I'm sorry, what'd you say, Dante?
He's still soft.
Oh, I thought you said he's still small. I'm like, are you blind? Well, then why did they sign it?
That's tough.
They didn't realize? Well, they'll find out. All right, derivatives. This is gonna be fun. How do you take the derivative when the variable is in the exponent? Here's the best thing about it, we don't care. You'll see why after a couple clicks. The derivative of e to the x is e to the x. It's its own derivative. Told you this would be easy.
So why do you take the derivative?
Well, you can still take the derivative, can't you?
Yeah.
You just get the same thing. When you take the derivative of e to the x, you get e to the x. Doesn't mean you can't take the, you can take a second derivative too. What's the second derivative of e to the x? The third derivative? Okay, so now what if we go backwards? What's the integral of e to the x? E to the x. We're done. Thanks for coming. A little bit. You gotta throw this guy in there. Don't forget, you got a chain rule. If it's not just x, you've got a function up there. Let's say e to the 2x. The derivative of e to the 2x would be e to the 2x, and you chain on the derivative of 2x, which would be 2. That's good.
So when you simplify the e to the 4x, because it's e to 2x times 2 e to 4.
No, the 2 would be in front. 2e to the 2x. The 2 doesn't go in the exponent. Easy peasy, right? You all look gun shy, like I'm gonna throw, like I'm gonna. There's no trick here. It's not gonna turn ugly all of a sudden. We're not gonna throw trig in there. It's just, I'm being honest. This is it. That's all you gotta do. Okay, so do that. Don't forget the chain rule. That's not just x up on top, it's a function. Oh, I skipped ahead. I guess I don't have the answers. What is the derivative of e to the negative, or e to the 2x minus 1?
2x minus 1.
Good. 2 times e to the 2x minus 1. Because the derivative of e to the anything is itself, and then you have to chain on the derivative of 2x minus 1, which is 2. Done. That one doesn't really warrant writing it down, but the second one might require a little bit of work. The only difficult part about the second one is the chain rule is not very pretty, but still doable. Itself times the derivative of this, which would be 3 over x squared, I believe. Bring that down to be positive 3 is negative 2. Which, yeah, there we go. Everybody okay with that? That's negative 3 times x to the negative 1. Negative 3 times x to the negative 1, which is, bring the negative 1 down, that's 3 times x to the negative 2. Put that back in the bottom and you get 3 over x squared. You could leave it like that if you'd like, it doesn't matter. Not much to do to simplify that thing, so you're done. It's just that simple.
Earlier on, you said we don't want to have negative exponents, so when does that actually start to apply then?
When we start doing more complicated problems. When you'll see some simplifying problems where you want to get rid of those negative exponents. Yes, sir?
It's kind of random, but when do we find the pool, like how long it takes to fill up the pool? Didn't you say we were gonna do it?
Yeah, to be honest, I forgot about it, but we can, I'll put something together, we'll use it as a review type thing. Bring your suit. Go swim. Not really.
Yeah, like an actual.
Okay, we know this already. The integral of e to the x dx is e to the x plus c. Remember, no chain rule. So if something is up there that's other than x, what must you do? U du is correct. Am I that loud?
She just stands in the closed.
No, she doesn't stand by the door. She stands in the class.
Do people in the front row like bleed from their ears?
No?
And I'm in the second row.
Maybe she wears a giant.
Well, she yells at Rachel for talking too loud in your 6th period class, so.
Say that again, I'm sorry.
She yells at Rachel in your 6th period class for talking too loud. So, not in the toilet, she talks too loud.
You're gonna tell her
Yeah.
she talks too loud.
Yeah, she
Well, you're gonna say,
she is
are you
real
gonna say you
aggressive.
talk too loud, or are you gonna say Mr. Reed said you talk too loud?
Probably the second
On my
one.
back.
Yeah.
And you're gonna wait till like in the middle of the lecture and just raise your hand and go, yeah, I got something to say.
Yeah.
What period are you over there?
I don't know, just tell you.
7th, right?
Yeah.
Yeah, I'm free 7th.
You better run fast.
Yeah, I'm coming in there to make sure you don't cause any problems. All right, do that one. Now, common mistake with these types of problems is you're going to say that it's e to the 3x plus 1. That's wrong. Okay. There is a factor involved that you, okay, let's try English this time, Rady. You need to do that as a u du. If you don't do the u du, you miss a constant for the answer. What's u? Yeah, 3x plus 1. So du is equal to 3 dx, so dx is equal to 1/3 du. That's what you miss if you don't do a u du. This first time I'm going to take you through the steps and do the replacement and everything else, but I think you'll realize early on that you could probably jump right to the end. That 1/3 is what gets lost if you don't do it the proper way using a u/du problem. So again, if that exponent is not just x, you're either going to have a chain rule if you're taking derivatives, Gesundheit, or you're going to have a u/du if you're doing integrals. We're all done. That's a Batman equation. There's actually a formula that'll graph that if you, I don't know what it is, but that's what happens when you graph it.
It's different. Those are all different.
They're probably all different functions. It's probably a summation of different functions. I would find it hard to believe that there's one function that generates that awesome picture. But if there was, it would be
Would you
fantastic.
get that, like, text?
The formula?
Yeah.
Yeah, just the formula, so people wouldn't know what it was.
Yeah, they'd be like, wasn't.
They have to plug it in.
What is that?
What do you mean?
Plug it into your
I think
calculator.
that might be a,
I
think that might be a slate on its own though.
Yeah.
Get that knowledge.
All right.